So the next talk is going to be given by Thea Aarrestad from CERN. So she's a senior research fellow at CERN working at the CMS experiments. And those of you who doesn't know what a CMS is, it's a compact muon solenoid. It's a general purpose detector at the LHC. And it has a broad physics program ranging from studying standard models, including Higgs boson, to searching for extra dimensions. So it's a really impactful work. And I think she will be joined with Clauidonor Coelho, who is the VP Fellow of AI and Head of AI at Palo Alto Networks. So please take it away, Tia. Thanks.
Hey, thanks for the nice introduction. You prepared well. Let me find the slides. So I'm assuming you see them now. All right. So
yes, we do.
Great.
If you go to full screen mode, that will be helpful. Thank you.
I think they should be. Are they not?
They are not.
No, they're not.
They're not. Okay, that is strange. Here, let me share my screen instead, then it's probably better. So there, now you should see my full screen instead of the keynotes.
Yep.
All right, great. All right, so as was just introduced, we are gonna present our latest collaboration on low power nanosecond inference engines for particle colliders. And I'm very happy to be able to co-present this together with Clauidonor, who's the head of AI at Palo Alto Networks. And we're both here presenting this on behalf of two great teams, so the old colleagues of Clauidonor at Google and my team at CERN. And we just released a preprint of the work presented here on the archive. So for any questions or if you want to look at something more closely, please have a look. So as was already introduced, the collaboration sort of started once we were looking into edge inference at the LHC. So CERN is home to the Large Hadron Collider, where it's the world's largest particle accelerator, where we collide protons at a center of mass energy of 13 TeV. So we accelerate them to the speed of almost up to the speed of light, and then bring them into collision at 4 different collision points. So at each of these collision points, we have particle detectors, like the one you see here. This is CMS. So there is a beam pipe in the middle, and the detector is kind of cylindrical around the interaction vertex, designed to reconstruct the particles emerging from the collision. So what happens in such a proton-proton collision is that the energy of the incoming protons are turned into mass, so new particles are produced. And these particles generate a spray of signals in our detectors around the interaction points. And our job as physicists is, to the best of our capability, to sort of reconstruct this full event, all the particles that were part of the collision. And as you can see from the image, it's not an easy task. So we have 200 collisions every 25 nanoseconds, 10 to the 3 particles roughly per collisions, 10 to the 8 sensors, and a data rate of 100, almost 1,000 terabits per second. And we have 1 microsecond or so to process each event. So the data processing is sort of the 2-stage approach. So first you have the collision occurring every 25 nanoseconds, so at 40 megahertz. And all the edge inference applications we're looking at here run on the detector itself, so on detector front-end ASICs. Then the full data gets fed into the level 1 hardware trigger. This is an FPGA-based farm where we select only 2.5% of the most interesting events. And the whole system has a latency of 12.5 microseconds with an input data bandwidth of 54 terabits per second. So everything here is FPGA ML inference. Then the data rate is reduced to 750 kilohertz, fed to the high-level trigger farm, which is a CPU farm, where we select 1% of all the events coming from the step before, and we have roughly 100 milliseconds or so to make decisions, so plenty of time at the HLT. Then the data is finally read out, is reconstructed offline and stored to tape. So nothing before here is stored. So we are looking at doing inference in 2 different places for sort of ultra low latency applications. One is on detector. So this is an area where we have extreme data rates and low latencies, as I mentioned before. What's also interesting is that this is on the detector, and due to the high radiation, we have to run the detector at low temperatures, so -20 to -30 degrees Celsius. And that means that everything that goes here has to be extremely low power because we can't afford more cooling in the system itself. So one of the things we're looking at for ASIC inference at LHC is to sort of represent the data more efficiently. So here you see a part of the detector, the high granularity calorimeter with up almost 30,000 silicon modules. And here we're looking at how we can use ML to sort of encode the information of the detector layers on ASIC and then decode them again on FPGA. And there's a limited bit width available. So we need quantization-aware training to optimize the information here in the bottleneck, and also to ensure that we have high accuracy in the decoder itself, because it will decode a lot of ASIC outputs in parallel. And then there's this low power aspect of it. We can't make it too hot. So a place where we have a little bit more time was the L1 trigger, as I mentioned before. What's crucial here is that all the events we do not select from here are lost forever. We cannot do any physics with them. So we need extremely high accuracy to keep the most interesting events, and the latency is low, between 1 to 12 microseconds. And here we want to do inference on FPGAs. The level 1 hardware trigger is kind of a farm of hundreds or so processors running large capacity FPGAs. It's located right next to the detector, so in a cavern close to the detector, and receives the signals from the detector via high-speed optical links. And the full system, as you see here, has a latency of 12.5 microseconds. Some things are done in parallel, some in series. So per algorithm, we're talking 1 microsecond or so. And as an example, in the final stage here, you have more than 1,000 algorithms running in parallel or on 10 or so FPGAs. So we want a workflow that can take us from floating point models trained with all the resources we have available to something optimally quantized. So based on the accuracy requirement we have and the resource constraints, so lower the energy by a factor of 2, we want the best heterogeneous quantization for that model. And then we want to translate it simply into highly parallel firmware and end up with an HLS project. So that's what we're going to present today. Claudio will cover the part here about automatic quantization, and I'll talk about the results and HLS. So please go ahead, Claudio.
Okay, thank you. So I guess you're going to continue to do the slide presentation, right?
I guess it's easier.
So, yes, it is. Thank you, Thea. And what we're going to be talking about here is what we call application-specific machine learning. A lot of people talk about programmable machine learning, but in this case, what we want to be able to do is to reduce the machine learning models as much as possible, and then specialize the subsystem, eliminate unnecessary routing resources, use different quantizations for each process element. And then the result that we want to do is to see what are the limits in lowering the performance and power, having like lower area, higher performance, and lower power. Next slide. How is this different from generic machine learning applications? Generic machine learning applications is what you would probably be running something like a ResNet 18 mobile net or something like that. But there are several cases where you just embed a very large number of tiny ML models inside an SoC or an FPGA. And those machine learning models are going to be good only for 1 or 2 or maybe like a handful of applications. Those applications are going to be aggressively quantized and optimized. And just to give an idea, when you talk about GPU machine learning, general purpose machine learning, we have latency in terms of milliseconds or more because of the memory subsystem. But actually at ASML, we want to basically tight integrate everything so that we can run at clock speeds. Okay, so programmability is another thing that it's interesting, because people say that, oh, we always want programmable weights. But then when you start talking to the ML engineers, they come to you and they say, how do you train those models? And they say, we use transfer learning. And then we have to explain to them that if they use transfer learning, they're actually already fixing some weights, and that those weights are not programmable. So we take that approach, and you can select, for example, if you want programmable weights or not, and for each layer. And our objective is to see the limits on how small you can get those machines. Thank you, Tim. Next. There's this paper by Kurt Coetzer that says that if you want really to quantize like very aggressively the machine, you need to have full control of the whole overall application. For just to give a few things that you need to look up in the model when you're training it in 32 bits, prefer to use ReLU 6 instead of ReLU, because since you're going to be doing quantization, you need to have upper bounds on the activation functions. In the original separable convolution 2D from Keras, there was no activation function between the depth-wise and the point-wise. So prefer to use the mobile net version that actually enables you to put an activation function, even if this activation function is to do clipping of the values. And just remember that the QKeras allows you to have like a very wide range of quantizers. And for example, we have very good experience in replacing some of the layers from mantissa quantization to exponent quantization. And exponent quantization provides with a very good trade-off between precision and dynamic range of the values. Next slide. So this is basically the overview of what QKeras gives. QKeras is available on GitHub, and it has a very large number of layers, and usually are those layers that we call like computational layers that you need trainable parameters or performs operations like multiplication and addition, because those are the ones we need to quantize. And it has we have a very rich set of activation layers. And for the sake of QKeras, an activation layer is just as the same as a quantizer. Okay, so you can see here that you have hard sigmoid, soft sigmoid, mantissa quantization, stochastic quantizers, binary and ternary quantizers, ReLU and hyperbolic tangent, and PO2 here actually means exponent quantization. Next slide. So if you just take this network, for example, and it's basically like a Keras example, and if you want to convert this to a QKeras, next slide, you're going to see that first, those layers you need to, every time that you need weights in the model, you need to replace by the quantized version. And everything in QKeras is about tagging the inputs and tagging the weights so that we know how to train in 32 bits, but faking to do a quantized training. And then we quantize the activations as well. So we quantize the inputs, quantize the outputs, and quantize the weights and bias. And in this way, even when we are training, we are actually doing the training in floating point, but faking the arithmetic model. So in this case here, we're just doing 4-bit quantization, 4-bit ReLUs everywhere. Next. And one thing that is interesting in QKeras is that it allows you to do mantissa quantization, for example, 2 bits, 3 bits, 4 bits, and etc. But actually, real gains, they come when you can replace the multiplication. For example, when you do exponent quantization for both inputs or weights, or when either the inputs or the weights, they are like ternary or binary, in which case you can replace the multiplication by just muxes. Okay, so if you look at this table, and from the exponent quantization on the diagonal going down up to the end on the far right, lower right, you can see that you don't need to do multiplication anymore with your operands. Next slide. So once we started doing quantizations, when we released the library first of all, you need to understand that every time that you quantize, the accuracy drops, okay? We're just dropping information, and when you drop the information, you can say, oh, but the accuracy dropped just by 0.01%. Yes, but it drops, okay, by a certain amount. Of course, if you want to quantize more aggressively, it's going to drop more than less. The thing you have to notice that when we start quantizing the networks, we realize that we had too many options to search. And it's a highly nonlinear problem that we want to optimize. And there has been several approaches tried before. For example, the previous presentation from Qualcomm, some approaches using reinforcement learning, random search, or Gaussian processes, trying to figure out what is the best approach to quantize a model. even like the work by Kurt Koitzer that was doing initially like hashing-based optimization. And hashing is worth mentioning here because when you do hashing-based optimization, they try to look at the curvature of the weight space. And if the curvature is too steep, that means you need more bits. If the curvature is smoother, then you would need less bits. But you have to understand that when you're quantizing the model, anything that you're changing in the model during training, it will affect the curvature space of it as well. So it's a codependent problem on analyzing the hashing and then trying to figure out how many bits you can use to quantize the model. Next slide. So thinking about that, we basically developed like a automatic quantization, push button automatic quantization method called AutoQKeras. And it basically has quantization selection. It has what we call forgiving factors. And it has filter tuning. What is filter tuning? I'm going to show you later that if you do quantization with filter tuning, you usually can get better results. And actually the implementation is based on Keras tuner, and that utilizes random search, Gaussian process, or hyperbands to search the best option. And just to give you like an idea, if you have 10 layers, 8 options for quantizations for kernel, bias, and output at each layer, we are talking about a search space of 2 to the power of 90 options here. So you can see that when the number of options is that high, doing a random search and sometimes even Gaussian process will not be able to converge very fast to give you. Like Google cloud companies, they may like that if you're doing a random search, exhaustive random search, but it may not be feasible. Next slide. So let's talk first about forgiving factor. Once I started asking the people that were the ML engineers, and I started asking this question, how much accuracy do you want to drop if I put deep quantization in your model? And as you expect, they will always say none. This is like a Brazilian Fiat 147, which was like a cheap car in Brazil in the 80s. And the idea here is that both are blue, by the way. And the idea here is this. You want to burn the power of a Lamborghini, but your budget is of a Fiat 147 for power. So think about that. You have this cell phone, for example, you want to put like an ML model on it, and you want to put like inside one of the SoCs. And people, when they say that they don't want to lose anything, what they're really telling you is this. My model burns the power for Lamborghini, but I want my model to be running for 24 hours on my cell phone without losing the battery, okay? So this is unfeasible. But because we got into this deadlock condition, we changed the question a little bit. Next slide. And then we ask this question. What if I reduce the power by 10x? Are you willing to accept a drop in accuracy of 1%? And amazingly, all those engineers, ML engineers that came to me before and they said they would not lose anything, they would start scratching their head and say, well, you know what? I'm willing to drop 1% in accuracy if you give me 10x more power, because instead of having 6 minutes of battery before my cell phone basically dies, now I can have 60 minutes of continuous usage of my model without losing any power. And actually, now we have two things. We have, for example, your accuracy of the model, and you have two models you need to compare. And how you compare two models with two different accuracies, but the models have different forgiving factors. So what we do, we multiply the accuracy by the forgiving factor, and we are basically forgiving the model for not behaving as well as the original model, as the reference model. Okay, so this is the equation that we came up with, and this is like the curve of the equation, and we try to penalize the model if it behaves worse, but we try to improve them to give like benefit of the model to correct the accuracy if the model if it drops a lot of the energy. Next slide. So I mentioned before state explosion, and in AutoQKeras we have 3 strategies to cope with the state explosion. The first one is limit the number of configuration options. For example, remember I had 8 options before, and if I reduce the 8 options to just 2 options in kernel bias and output quantization with 10 layers, I'm talking now about a search space of 2 to the 30 options. But we have other strategies to make the system, the search converge. The other one is group layers by the same quantizations. For example, instead of 30 layers, I want to group the quantizations to just 3 different groups with 2 options each. Then our search space drops to 2 to the power of 9 options in this example. And most often we end up using the last one, which is instead of doing the quantization in parallel for all the models or all the layers and all the options to quantize, we perform this serially. For example, we can choose the model that burns the most of the power, the layer that burns most of the power, quantize that model first exhaustively, then goes to the next one, the next layer, then goes to the next layer. And in this case, you can see here that we remove this 10 from the exponent here to be like sequential. You just have to remember that this is an approximation, but it makes the system converge. And we get good results. Next slide. So this is an example how you limit configuration in AutoQKeras. And in this case here, you can say that we're doing like 1 bit, even stochastic quantization for kernel bias activation. And linear here refers to when you need a layer, activation layer, just to cut the number of bits, for example, in the case that I mentioned between the depth-wise and the point-wise convolution. And limit here in the dense layers, I'm saying just use 8 bits for weights, bias, and 4 bits for activations, for convolution, 4 bits for weights, 8 bits for bias, and 4 bits for activations, and so forth. Next slide. So group by name, when you specify the problem in AutoQKeras, you can just put regular expressions on the layer names. And in this case here, I'm just limiting I just want to try those convolutions here, convolution that has the 0 in the name with binary, ternary, and quantized bits 2. And for the convolution layers 1, 2, 3, 4, group them together and use either 4 bits, 8 bits, all 4-bit configurations, 8-bit biases, and 4 bits for activations. Next slide. And finally, we can create blocks of layers, and we can quantize them by group, like either sequentially or by cost. And by cost means I pre-compute the energy estimation for each one of those blocks, and I pick one with the largest energy first, then I pick up the second one next, and so forth. But for ResNet 50, that may not work very well, so you may end up, for ResNet type of network, you may end up doing the sequential. Next. So this is, just, can you go back one slide? There's something that I forgot to mention here that I just want to mention. I talked a little bit about filter tuning, okay? And what is filter tuning? Suppose that you're quantizing the network aggressively to 1 bit, for example. What we started realizing is that two set of filters in a convolutional layers, after quantization, they could end up with the same filters, okay? So in that case, it would justify to lower the number of filters. And in some other cases, if I increase the number of filters a little bit more, I'm able to quantize even further the number of bits. So I just gave you reasons why I could either increase or decrease the number of filters on a layer. And in general, I cannot tell you if I have to increase or decrease the number of filters. So what you can do in AutoQKeras is you can actually turn on filter tuning, that it will wiggle around your original network, the number of filters up and down, so that you end up in a configuration that you drop more of the energy. Next slide.
Time check, 10 minutes.
Okay, thank you. And you can see in AutoQKeras this nice Pareto curve here, a Pareto frontier, where you have the model accuracy and the number of bits, and then you could select the one that has the highest accuracy and the model size. Next. And this is like another experiment where you can say that if you can actually select this Pareto frontier curve here that has the largest accuracy and the smallest number of weights. And with that, I can turn this back to Thea, and she can continue the presentation.
Thank you. Yeah, so as Claudion said, we are one of those places where we do accept a small loss in accuracy if it means we can keep our detector from radiation damage. So it's essentially the workflow we're using now, we want to use now, is using AutoQKeras to find the best low power solution, giving some accuracy requirements that we have for that application. So how much data we can afford to collect, for instance. And then we want a way to translate that QKeras model into firmware easily. And for that, we use HLS4ML. And HLS4ML is a library. It stands for High Level Synthesis for Machine Learning, and it's essentially a library for translating Keras, TensorFlow, ONNX models into firmware. And it works in the following way. So you start with some model, you compress it offline, so using AutoQKeras, QKeras pruning in an iterative way until it's reached the desired size. Then you do the HLS conversion, where we do allow for the project to be further reduced in size through post-training quantization. But in this case, now when we use QAT for the compression itself, we just translate the configuration from QKeras into the corresponding fixed point precision. Then you can tune the reuse factor to either lower the latency or lower the amount of resources you use. And in the end, you have an HLS project you can use as a co-processing kernel or for custom firmware. So after running AutoQ on a typical sort of benchmark problem at CERN, particle identification, we trained a simple 5-output multi-classifier and ran the model through QKeras. This is what we came out with. So each layer is quantized separately with a bit width at maximum 4, and we have ternary layers, binary layers. And so it's a really small model. On the bottom, you can see the full model configuration and the energy estimate of that model using QTools, which is part of the QKeras library. So 0.9 nanojoule of energy, so it's a really small model. Then the results we obtained with QKeras is shown here. Here you can see the model accuracy with respect to the floating point model as a function of bit width for homogeneously quantized QKeras models. We have a high accuracy down to a bit width of 5 or so. And then with the AutoQKeras model, the accuracy does drop a bit, but we did allow it to drop. And on the right-hand side, you can see the resource usage, the lookup tables, DSPs, and the flip-flops. And we see they really go down as a function of the bit width. And at around a bit width of 9, all the multiplications move from the DSPs to the LUTs, which is good for us because we usually have way fewer DSPs than lookup tables. And the most efficient model is the AutoQ model. You can see the summary in the table here. The latency is roughly 50 nanoseconds with the resource usage 98% smaller than the baseline model. So to summarize, I'll give it back to you, Claudio, to wrap it up.
Okay. And what's very interesting of this collaboration is that we end up with an end-to-end push-button synthesis flow from ML to hardware. Okay, we have AutoQKeras and AutoQKeras for quantizing machine learning and deep learning architectures. And the latest version of QKeras include RNN networks, but we have not done much work trying to quantize those networks yet. But we know that we need usually more bits for RNN for initial experiments we did. We use AutoML to automatically do the trade-off for you between accuracy and model size and energy, including the filter tuning. And that gives you very aggressive architectures. And we have this integrated with the fully integrated with HLS for ML at this time.
Great.
With that, we conclude our talk.
Thanks for listening.
Awesome. Thank you so much, Thea. Thank you so much, Clauidonor. Any questions? We have 5 minutes, so that's great timing. Thank you, guys. Please raise your hands if you have questions. Okay, well, we are waiting. So can I ask that I have a question. So is this publicly available, the AutoQKeras tool, or you guys are thinking of, okay.
So if you just download the AutoQKeras from GitHub, there is a notebook that has all the fully explaining how to do the automatic quantization inside the QKeras spec.
Okay, cool.
Oh, sorry.
Yeah, and HLS for ML can be also downloaded. Okay.
Yeah.
I have maybe it's like a more practical question, but just out of curiosity, because you have like how do you actually deploy? So if you take a model and then quantize it, or like try to quantize maybe to a smaller bit width to see if you can squeeze out more performance, how do you actually like verify and deploy that model? You know, since you can't obviously like just deploy it to the collider, I guess, like because it's very expensive, I imagine, to run an experiment. Like, what is that kind of like process like?
We have test benches everywhere, so we translate it with HLS4ML, we deploy it on FPGA, and we test the accuracy and measure all the benchmark numbers we can. So we do it on test bench on the same FPGAs that we have in the system.
I see. So is it really just like an end-to-end if you can just sort of replicate like your accuracy score?
Yeah, you usually would just have to make sure that it should, for everything we've seen so far, the translation, once you put it on firmware, works fine. So we evaluate, of course, again, the same model accuracy check that is the same as offline once we do test the workflow. You should do that if you see something fishy yourself, but that's how we do it ourselves. Yeah. So we test the flow, make sure it's okay, and then put it in.
Yeah, what I have seen on the QKeras model as experience is that when you see that the model has a difference in accuracy, you end up realizing that that's because you forgot to quantize one of the models and there's some hidden operation inside Keras that you did not realize. For example, if you do global average pooling, there is like some operation executed inside the global average pooling, and as a result, that should be quantized as well. Okay.
Yeah, I mean, it's really sensitive to that. Once you put it on chip, it's quite sensitive if you have these sort of jumps in precision when an output goes to an input. So yeah, that's things you have to be careful with.
Yeah, thank you. And of course, we have the paper there. The paper has much more detail on the how we are doing the implementation and the problems they can find.
Yeah, also, HLS4ML has tutorial on the full workflow, so quantizing with QKeras and then deploying the QKeras models. That we would be happy if you try out.
Awesome. Yeah, there are some follow-up. People want to follow up with you guys, so please feel free to reach out to others who are listening. I think there is another question on any plans to use the custom tensor blocks in the Intel or Xilinx FPGAs in combination with QKeras.
Say again, any plans to use them?
Custom tensor blocks in the Intel or Xilinx FPGAs in combination with QKeras.
So what are you calling like custom the tensor common tensor blocks?
This is a question from Shreyas Ravi Shankar, so maybe I'll let him follow up. We have 10 seconds, so maybe it's time to move on. So thank you again. This is a great presentation. So if I would just request if you put the link to the paper and the HLS4ML.
I'll put it in the chat also.
Yeah, that will be super helpful. Thank you again.
For any questions, please reach out in private.
Yeah, if you solve